Login accepted.
Hello, everyone. Thank you for coming to the talk. I see very patient people here because this is the last talk of the conference. So today we're going to talk about the architecture, and I will give example of the real product that I'm responsible at Playtika. And this journey of the architecture evolution of this product took 9 years, but today we will do it in a 50 minutes. So we will kind of do a retrospective of what has happened, how architecture was changed, and why we did what we did. My name is Kanstantsin. I'm a software architect at Playtika. I'm responsible for the backend architecture of the games. And today we're going to talk about the mobile game, Best Fins. It is the match 3 game. Actually, this is the product you can play in download. You can do it even now. So there is built in Apple Store. There is a built in the Play Market. So the game has more than 50 million downloads. So it's already a big scale. There are a lot of players, a lot of daily active users. And the journey will take us from the moment when it was a startup, like 9 years old, up to the moment where we are now, and we will see the evolution of the architecture. I splitted this evolution into the 3 logical stages. Let's call it architecture 1.0, architecture 1.5, and architecture 2.0. And we will review those architectures and figure out how the system was changed. So we are not going to talk about implementing of every feature in this game. We're mostly talk about the quality of the system to incorporate new requirements, to grow, to evolve. I will give a few examples of some features, but mostly to explain the design patterns we have used, but not covering of all the functionality, all the features of game is not in scope of this talk. And I want to recommend this book. This book inspired me a lot. This book is about coupling. So when I started reading this book, I realized, OK, this is all about my project. All types of coupling that were in my project. So the software often starts small, especially if we are working on the game market, because when we design a new game, we creating some new story, we creating designs, art, and we don't know yet if this game is going to be popular. So we want to create something, then we want to publish it, we want to get the feedback from the players, we want to improve it, and this is like a cycle of continuous improvement. And at this moment, we are not going to invest in a complex architecture until we prove that this product has a value. Because making successful game is there is a lot of luck in it. So the goal of the architecture 1.0 is quick prototyping. So at this moment, the architecture will help us to prototype. And architecture 1.0 of this game is pretty simple. So we have 3 monoliths. We have client, we have server, and we have back office. And those 3 monoliths implementing some functions. The client contains all the business logic. So we want to play the game, we want to play the levels, collect some scores. It's all on the client. Client, at this moment, responsible for player data as well. So server implements a few business functions. For example, user login, server collects analytical events, and handles the player data backup. So server is just backup for the data. So there is no business logic at server in this moment. It's very client-centric application with fat client monolith. And back office allows to view the data we have on the server. So technology stack is the following. So we have Unity, is the cross-platform framework for developing the mobile games. So we write it in C#. We can build it for iOS, for Android. We using Google Cloud at this moment. We used Google Cloud. And we used most of the managed services. So we didn't want to think about how do we deploy it, how to scale it. We wanted to think about the product. We wanted to keep prototyping, keep adding new features to see if this product even having a value. Should we even invest more into this? And we have Elasticsearch on the back office to store the logs, to store analytical events, to collect this data. So that was the architecture 1.0, pretty simple. It's allow us to quickly prototype. It was the monolith with no boundaries. And then we're moving forward to the architecture 1.5. So what happens when the business value is proven of the software? So assuming we already published this game in the market, players love it, so a lot of people playing it, like we want to invest more into this game, and therefore the team is growing. So when the value of the product is proven, the business is hiring much more people to add, to enhance, improve this product. So at this stage, we have many more stakeholders, and we have a few feature development teams which implement in the change requests of those stakeholders. So we have a lot of changes in this product made by a lot of people in parallel. But the architecture 1.0 is monolith with no boundaries, with no even modularity. We didn't care about it at this moment. So the goal for architecture 1.5 is actually provide ability for a lot of people to do a lot of changes in parallel, to kind of unlocking this parallel deployment and development and releases. Before we go into the technical solutions, let's a little bit talk about coupling, because this is an important topic here. So basically, coupling means if two components are coupled, they are connected. If components are connected, they're supposed to share some knowledge, or they're supposed to share some life cycle. For example, they have to be deployed together, and you cannot deploy those components separately. If we have a tightly coupled system, it's much harder to do changes of those components by multiple people at the same time. For example, let's talk about two components, A and B, and those components are communicating through well-defined API contract. So in this case, changes can be done in component A without touching the component B and vice versa. Those components share minimum knowledge, so like two independent teams can work on them in parallel and don't interfere to each other. On the other side, if we have more tight coupling, like functional, model, or intrusive coupling, so components depending on some internal implementation details or depending on the model, and changes of the component A is highly likely to trigger the change in component B. And those components are harder to develop in parallel by multiple teams. If we're doing the microservices and micro apps, then we can release each microservice and micro app independently. So there could be 3 engineers or 3 teams working on this in parallel. While if we operate with monolith, even if the monolith is modular, so basically models of the monolith have strict context boundaries, they share minimum knowledge, but anyway, those models have to be released together. You cannot, if you change in module A, you have to release the whole monolith. You cannot do independent releases of those. And the content. So assuming in the application, you need to show some graphical content, video, sounds, text content, so any content, and especially in the game, we have a lot of graphical content. So in case the content can be downloaded remotely, we can publish a new content without the releasing the application. So basically, content and application, they have independent release cycles. If we're using a static content, a static configuration, we have to include it, we have to build it, we have to publish it. So we cannot release the new content without the application release. So content and application have a shared release lifecycle. So we discussed a few design patterns, mostly talking about shared knowledge and shared lifecycle. So basically for developing those products in parallel by multiple teams, we would prefer independent knowledge. So components are communicating through some API contract, and independent lifecycles. So we can deploy these components independently. And let's go back to the business. So I've took a few features at this moment, which we have to implement, and show how we will implement those features using those patterns. We're already talking about content. So when we have some application, we want to show some graphical files here, some video, play sounds, we have to include this content. In case of the game, it could be some new mini games we can include, like new runs. For example, we want to run a tournament for Halloween, and we need to provide a graphical reskin of the game so it looks like Halloween. Also, the levels is example of the content. So we want to add new levels in the game, but we don't want to rebuild the game every time we're adding new levels. So basically, the goal is to move from the static content release to remote content release. So we, instead of including those content into the build, testing it, publishing it, we want to upload it somewhere and not depend on application release at all. So we started building the content management system. Let's assume we have this client monolith, and this monolith has a static content, static configuration included into the build, and we also need to put the launch schedule in the build as well. So basically, at some particular date, you should run those tournaments. You should change your application graphical interface. First of all, we extract content and configuration and put it somewhere remotely. For example, we can put the content on CDN, upload these graphical files, and we could build a new microservice, let's call it configuration service, which provides the configuration and also handling the logic of the launch schedule. So whenever application connects to the service, it asks, OK, do I need to start a new tournament? Do I need to show a game? And configuration service provides the data. And we started building micro frontends, micro apps. So instead of including the new functionality in the monolith, we just deprecated the monolith. So OK, monolith still exists. We probably have no time to split it, to rewrite it. But whatever we built new, we built a new microservices. So we built a configuration service. We deployed the micro frontend container. We started building the apps. We're not including those apps into the old back-office monolith. So we did it in order to release independently and develop by multiple teams at the same time. So the player segmentation, this is another use case. Assuming we want to split the players by populations and run some different logic, run some different configuration per population. For example, tournament is a good example. We can do multiple leagues in the tournament and let beginners play with beginners and experts play with experts. In order to segment the players, split the populations, we need to collect the game events, put them into some cache, and then evaluate some business rules on top of this data. So we understand, OK, this user belongs to population A, and that user belongs to population B. And we started building the segmentation system. So there is already the configuration service, which we discussed before. So the application can download configuration from this service, and configuration is provided for a whole population. Assuming that we want to provide two different configurations, one for population A and second one for population B. So we put those two configurations into the configuration service. And then we need to decide, OK, depending on the population, for example, user belongs to population A or population B, we provide one or the other configuration file. So we built a segmentation service which contains those rules. And segmentation service actually tells us what is the population this user belongs. And we need to feed the data into the service somehow. So we already had this server monolith, which was hosting the player data backups. So what we just need to send those backups to segmentation service. So segmentation service can use this data and evaluate the population. And of course, we built a new micro app, adding those to micro frontend container. So another feature is the social mechanics, especially the tournaments. So social mechanics is pretty powerful tool to engage the players into the game. So people like compete to each other, people like sharing results to their friends. And tournaments are done using segmentation. So if you are a beginner player and it's not interesting for you to compete with very expert players, right? And vice versa. And we could also get different rewards if we participate, if we win different leagues. So we started build the tournaments. And this is when we change in the concept. So previously, we used to build business logic on the client. It was fat client architecture. But tournaments is a multiplayer feature. It's really hard to build a multiplayer feature on the client. So we built a tournament service and put business logic on it. So basically, we have a first feature when we have business logic on the server, and client is just more light. It has view only. And tournament service is also responsible for handling all the player data. There could be scenarios when we're going offline. For example, like there is no internet or there is a partial internet loss, like we are riding in a bus or in a metro, and for a short period of time, the internet connection drops. So we need to handle it. We are not going to lose the tournament scores in this moment because that would be unfair. So we also introduced kind of a buffer of commands which we can store on the client. And then when connection goes up, we send those commands to the server. So actually, we send those tournament scores. So this is kind of a partially online architecture. So this is a feature which is working online, but for some period of time, you can also play offline by collecting your scores. Of course, we need to add the segmentation system because we want to split the players into the leagues. And we want to build a new micro app in order to manage those features, to configure, to see some statistics. And the infrastructure optimization, that was one more business driver, like maybe more technical than the others. So initially, I've told that we started with the Google Cloud. And Playtika has their own data centers and their own infrastructure. The managed infrastructure, we call it Playtika Cloud. So when we build something new, we didn't build it inside the Google Cloud, we built it in Playtika Cloud. And finally, we got kind of a hybrid system when part of the game is hosted in the Google Cloud, another part of the game is hosted in the Playtika Cloud. So that solution became pretty complicated to maintain because we need engineers with the skills in Google Cloud, we need to engineers with the skills in the Playtika stack. There are some data synchronization is needed, some latencies, like whatever. And decision was made by business to migrate all the infrastructure into the one data center, and that will be Playtika Cloud. So we have to rewrite the code because initially the code was written with a maximum vendor lock because we have to prototype really quickly. We didn't want to think about how it's deployed, how it's scaled. In Playtika, we're using Spring Cloud on top of Kubernetes. We're using Kafka, and we're using Aerospike as the key value database. So we have to rewrite all this monolith into this stack. And we started the data migration project. So assuming we have system hosted in the Google Cloud, so there is a client, there is a server, it is connected, and we have a player data in the Google Cloud. So we rewrote this system into the different stack and hosted like similar system in the Playtika Cloud. So now we have two systems with the same business logic. Then we started data synchronization. So we created a migration service which consumes the data from the Google Cloud. And inside the server monolith on the Google Cloud, we've put an update logger. So anytime we change in some data structure, we write into the database. We also write in those events into the update events queue, which is consumed by migration service and then stored in the Playtika Cloud database. So whenever we are writing to the Google Cloud, we synchronizing this data to the Playtika Cloud. And we implemented the reverse process. So we created kind of a dual write system. We can write to any data center, and eventually the data will be synchronized to the other. So then we created a URL dispatcher on the client, which we can control, and we can switch population by population, and finally turn off the Google Cloud infrastructure, migrating all users to the Playtika Cloud. So that was the migration approach. We started with active data sync. So whenever a user is connected to the game, playing the game, whenever some data is updated, we synchronize on those updated data. But there are users who didn't log in, for example. There is also a lot of data. It's a passive data. So we implemented some tool that scans the whole data set and initiates the synchronization process for the passive users who didn't log in or the data was not changed. We implemented the tool for discrepancy analysis to compare the data between two data centers, and we done a technical test. So we switch a test population to the Playtika Cloud and then roll it back. So we also tested the rollback scenario. So what are we going to do in case something goes wrong? And we migrated population by population. We did a gradual migration. There are some numbers. So we are engineers, we love numbers. We did it with zero downtime, migrated 50 terabytes of player data from Google Cloud to Playtika Cloud, and significantly reduced the infrastructure and maintenance costs. So let's do some recap. So this is the architecture 1.5. As you can see, we didn't touch initial monolith. So we just deprecated it. So it's still working. It's still hosting the player data backup. What we have done, we just ported it to the Playtika Cloud and migrated all the data. We also added the platform services. So we have configuration system, we have segmentation system. We added the micro front-end container and start building the micro apps. So we do not add this functionality in monolith anymore. And we introduce the new types of features when we have a business logic on the server. So right now, it's not only the tournaments, and the client for these features becomes lightweight, containing mostly Vue. And those domain services are handling business logic and player data. So this is architecture 1.5. The purpose of this architecture was to scale for multiple parallel teams, multiple stakeholders, so we can implement more changes in the system. And therefore, we introduced microservices, micro frontends, and we separated application and content releases. So we don't have to release new application, upload it to the stores in order to publish the new content. And we are moving towards the architecture 2.0. So the driver for architecture 2.0 is complexity growth. So whenever we add a new functionality, and functionality grows linearly, the complexity grows super linearly. And whenever we add in a little bit more functionality, we are reaching to high complexity and struggling here. So what is the source of this complexity? First of all, we're talking about coupling, yeah? And if we have cascading changes, for example, you change in one place, and you have to check in everywhere else, or if you want to change one aspect of the game, but for this one, you have to patch it everywhere, this is cascading changes. It's really hard to keep control over this, and it's really hard to make it stable, especially if multiple teams making those changes in the parallel. Also, we've noticed that we're developing the similar solutions from scratch. I actually talked to many people, and many people admitted in their organizations it happens as well. So there are multiple implementation of the same thing done by multiple teams. And this causing a huge cognitive load, because we need to think about if we're making a change, the change will be cascading to many other places. We need to check it everywhere. We need to keep it under control. We need to design every feature from scratch, thinking about the same topics again and again, developing, so that causes a high cognitive load for us. So the software actually doesn't fit in the brains of one engineer. It's too big to understand. And the goal for the architecture 2.0 is to introduce something to reduce development complexity, to make sure we can continue developing features while complexity doesn't grow super linearly. And we want to scale the organization. So for example, we want to build more features, we want to add more teams, but do not increase complexity. So to define the architecture 2.0, first of all, we revisited the system context boundaries again. we defined the feature design standards and built a generic reusable solutions. So let's talk about the context boundaries. Basically, context boundaries is one of the most important things in the system design, because when your system gets big, it is too big to fit in one person's brain. So it's really hard to make the system, like to maintain it, to improve it. Anyway, we have to split our code into modules, services, like whatever. We need to isolate the context, and we need to decide what is in, what is out, and what is communicated between those modules. Any big system comes to this problem. So initially, in 1.5, we had the client directly communicating to the platform services. In case we're making any change in the platform service, we have to make a change on the client. So clients need to directly know about everything we have on the backend, about every service. So we decided to go with the backend for frontend. So basically isolate the client and server responsibility. So whatever client shouldn't know is hidden on the server side behind the backend for frontend. And client may not connect to platform services directly in the architecture 2.0. In 1.5, we introduced microservices. So microservices solve the problem of independent releases. It's like a physical boundary between code bases. But they're not solving the problem of like reusing the components, reusing the code. It's not their purpose. So in 1.5, we have to repeat. We have to develop every feature from scratch, introducing similar solutions. And in case we want to change some common aspect in the game, we have to go and patch it in every feature. So this is actually called cascading changes. In 2.0, we decided to build a boundary between the features, the business logic, and between the platform. So platform is kind of a set of some common components which can be reused across the features. We call it feature development toolkit. It's kind of a framework. So if we have some problem and we need to solve this problem again and again for every feature, we could extract it into the reusable module and keep using it. So when we build in the features, we are mostly focused on business logic, how to make this feature interesting, attractive, but we're not focusing on the tech decisions. And we're not focused on the boring work, which we can extract as generic component. In case we need to change some aspect, which is implemented on generic component layer, we don't have to go to every feature and patch it. So those are the context boundaries. We separated client and the server. We separated feature and the platform. And then we analyzed our system designs for like last maybe year and a half, found like the patterns that we used, and created like a knowledge base of some good solutions we already used. It created the architecture blueprints. We call it feature design standards. So whenever you need to implement new feature, you don't need to reinvent it. You just go to the knowledge base, to the blueprint, and do it according to the blueprint. And blueprint contains already the best solutions we have done. So according to the standards, we classified features into the two groups: the online first features and the offline first features. So the classification is done based on how much user interaction is required. So in case we are not required to do active user interaction, or we do multiplayer, we can go with online first and put business logic on the server. In case we are doing some in-level mechanics, something very interactively, we cannot afford the server calls, so we need to build it on the client. For online first features, those features require the internet connection to play. So we always need to make a server calls. It could be some limited functionality offline. I've shown you this event buffer, so we can collect some commands in the buffer and send those commands to the server. But server is source of truth for the player state. So that means in case we are offline, we can do some computation offline, but whenever we synchronize the data to the server, then we trust the server. So client can temporarily be like source of truth, but until connection is restored. So this is the online first architecture. This is something we already familiar. We just put the layer that is responsible for communicating to the server to the library, we call it partially online toolkit. So whenever we need to communicate to server, we use this toolkit. And the purpose of this toolkit to cache the data, like pre-warm it, preload it, and provide this buffer and synchronize this buffer. So basically, we can load enough data on the game startup, and whenever you open in some feature, the data is already available, you just get it. So we are not fetching the data in the moment when we open in some feature, to not introduce the network delays. And the offline first features. So offline first feature, they require the internet connection to download the content and configuration. But then, when you download it, when this is in the cache, you can play fully offline. And the client is source of truth for the player state. So client calculates the data. The data could be sent to the server. Server could store backups. Server could use it for segmentation, but server is not able to modify the data because the client owns it. So this is the offline first architecture. We've put a backend for frontend between the client and platform services, but we keep everything else like architecture 1.0. So there is a view, business logic, and player data on the client. And we took some common solutions that we repeatedly developed all the time in the different features and extracted into the common components so we can reuse those components in other features. For example, the way how we earning some rewards in the game. So when we play in the game, we can earn some rewards, and we can spend those rewards, for example, for upgrades, we can spend them in levels. So actually, game is about like earning and spending, about balance changes. And we figure out that each feature has some specific implementation of this rewarding flow. So we keep doing it again and again. And therefore, in case, for example, we need to change some cross-game aspect, like we want to add a new type resource of the game, we need to go to every feature and patch it, because it's done slightly differently. There is no common layer handling those rewards. Each feature done in a unique way. So in case we want to collect analytics, we need to always create a new ETL pipelines to parse the data, and there are many consequences like this, because there are multiple implementations of the same thing, and we spend an extra effort to support in those implementations. So we came up with a rewarding toolkit. It contains of the configuration system, the UI components we can use everywhere that are able to display any type of rewards. The components responsible for transaction flow. It's transaction with the virtual game resources like balance increase, balance decrease, and unified analytics. So basically, whenever we develop a new feature, we are not implementing those aspects again. We're just using existing components. So we introduced a new component on the client. Let's call it wallet. And features must talk to wallet in order to spend or earn resources. For example, you want to increase the balance or decrease the balance. You cannot exchange the resources directly between the features. But the features have to use unified UI components. In case we want to send the reward that we earned on the server, for example, we were playing the tournament and we won the tournament, want to give a reward, we store it in the outbox. So we call it bonus service. So basically, it is the service which stores information about received rewards until the client connected and fetch these rewards from this outbox service. And client can record the new balance in the wallet. And we implemented the flow back. So in case we want to send some resources from the client to the server, for example, I don't know, we are offline, so we cannot call the server in this moment. We stored those resources in the balance buffer. And then when internet goes up, we flush this balance buffer. We added this inbox component on the server side. We call it goods router. So it receives those new resources and updates balance on the server. So basically, right now, all the features are using this system in order to exchange the resources between each other. So we don't have to implement it from scratch. We were talking about the player state synchronization. So we have like offline first features, online first features. offline first features responsible for the player state, there is the client area. For the online first feature, there is a server area. And basically, we figure out that, OK, also each feature has a specific implementation of the player state synchronization. So sometimes it's not happened fully asynchronously, so we could have some game freezes in case, like in the moment of synchronization, the internet goes slower. Could be some temporary data discrepancies. And what's important, there are extra efforts for supporting the multiple implementations. And we already talked about this layer. It's partial online toolkit, which is responsible for the data caching and storing the buffer of commands in case we are offline and we need to synchronize it later. So there is also a component we're going to reuse. And we reviewed the game operations flow. So what is the game operations flow? Assuming we want to run a new tournament. So first of all, we need to configure those tournaments. For example, configure like what's going to be the leagues, what's going to be the rewards, how many users we allow to play, like all this segmentation specifics. Then we need to do some pre-launch verification. So for example, we enter the tournament before it started for users and check if everything is configured properly. And then we're launching it. So tournament is available for users. And then whenever you start playing, this configuration should be sticked to you. So basically, even if we update the configuration, the users who already entered the tournament should not have any changes. So only the new users receive the new configuration. So this is like the flow which like supposed to be generic for all the features. But we figure out that each feature still has specific implementation of the game operations flow. And some features may not have stickness or may not have pre-launch mode, which makes it pretty hard to test it. And as a consequence, it requires extra efforts for supporting those multiple implementations. So we reviewed the configuration system in architecture 1.5 and found out that this pre-launch API, for example, we want to enter into the tournament before it started, like it is done in own way in every feature, plus the stickness also is done in own way in every feature. So this is on feature layer. And whenever we build in every feature, we need to repeat those functionality. So in 2.0, we decided to put those capabilities into the configuration service. So basically, it's done once. It is a one implementation, which is the same for all the features. And if we want to build a feature, we don't have even to think about it. So the architecture 2.0 still contains the architecture 1.0. It's still those monolith. We didn't change it, except like rehosting to the Playtika cloud. We just deprecated. So we didn't add any new functionality into this monolith. The architecture 1.5 included a lot of stuff like platform services, domain services, and micro front-end container like micro apps, and the features on the client which do not have like business logic. It's mostly view only, the features with the business logic on the server. And the architecture 2.0 is improved the boundaries by adding the backend for frontend. So client no longer connects to platform services directly. Client connects to monolith, backend for frontend, and the feature domain services. Plus, we introduced this feature development kit, like a lot of small reusable components. And it's also important to mention about the social technical system, because without changing the organization, the team structure, the architecture 2.0 wouldn't be possible. In 1968, there was an article, I'm pretty sure many of you are familiar with this statement. So the organization system design is kind of a copy of the communication structure. And Conway gives an example when there were two developer teams. One is 5 engineers, and they implemented a compiler which has 5 phases of compilation, while the 3 engineers implemented the compiler for 3 phases of compilation. So this is how the architecture reflects to the organizational structure. So in case the Conway law is true, and management defined the software architecture, basically we need to use some management techniques to promote the right architecture. And in our case, the current team topology didn't promote this architecture, didn't force us to build the reusable components. So assuming there are autonomous teams, and each team is kind of having their own backlog, having own goals, like own product manager, they're not much interested to communicate to each other to create some generic solutions. This is why we have consequences, so each feature has a custom implementation of something, and there are extra efforts for supporting those multiple implementations. So we decided to apply some management principles to the architecture. It is called inverse convey maneuver. So we evolved the organizational structure to promote the desired architecture, because those generic components, there should be some ownership on it. And it could not be done by these autonomous feature teams because they are focused on solving the business problem. So we created the architecture transformation team, which is supposed to build those toolkit and prove it. So create those components, try to use it, implement in some features, make them stable, and provide those components to the feature teams. And feature teams should be focused on business logic mostly, reusing those components. So we walked through the evolution of the architecture, which took already 9 years, and we'll keep going. We started with architecture 1.0, which was done for the purpose of the quick prototyping. So at this moment, we didn't know if the product has a value, if people like the game. So it makes no sense at this moment to build some complicated architecture. We just need to prove the idea really quickly. Then, when the business value was proven, there was a lot of new people joining the team, a lot of new stakeholders, a lot of new feature requests. And we focused on solving the problem on parallel development and releases. So we introduced microservices, micro frontends, and we separated releases of the application and content. So we were not using the static content anymore. The content is downloaded from the remote server, and the content team and the application team are not interfering to each other. And the architecture 2.0 solved the problem, solving the problem, we hope solves the problem of the extra complexity. So the architecture 2.0 is about standardization by introducing some feature design standards like blueprints and building those feature development toolkit, a set of reusable components, so we can focus on features but not on the tech decisions. And for the architecture 2.0, we also have to apply the inverse convey maneuver to promote the right architecture. Thank you very much for your time. If you have any questions, I think we have 7 minutes, or you can talk to me later after the talk. Thank you. Have a good day.